AI clusters are now capable of pushing light at exascale velocities, yet the actual efficiency of these clusters often drops as the physical bandwidth increases. The industry has largely solved the problem of raw data movement. Hardware manufacturers now deploy 800 gigabit to 3.2 terabit optical transceivers that deliver flawless, lossless data between nodes. But the system hits a wall the moment that data leaves the optical components and enters the top-of-rack switch or the data processing unit. At this point, the network relies on legacy semantic protocols like BGP and deep packet inspection firewalls. These systems must open and interpret the data payload to determine its destination and security status. This parsing process is computationally expensive. Reading and routing packets consumes up to 30% of the switch's CPU cycles. That friction creates a traffic jam. The resulting microbursts and jitter propagate through the fabric, directly impacting hardware performance. When the network cannot parse the logic fast enough, attached GPUs are starved of data, resulting in double-digit degradation in model flops utilization. Traditional network architecture is built on the assumption that optical transceivers are passive conduits, while all active routing logic must live at layers 3 and 4. Preventing these cluster bottlenecks requires pushing network intelligence down the stack to layer 1. This white paper proposes a shift from semantic logic to deterministic physical geometry. It outlines the integration of tensor networks' predictive tensor control plane and quantum gravity mathematics directly into Coherent's optical DSP firmware. This creates topologically intelligent optics, allowing the physical layer to autonomously execute security and routing tasks. This transformation takes place inside the digital signal processor, housed within a 1.6 terabit coherent transceiver. There are two ways of processing data: semantic logic and geometric topology. Semantic logic requires a CPU to open packets and read IP headers. Conversely, the coherent DSP's topological model evaluates telemetry as a continuous wave, compressing it into a bounded probability tensor. Because the DSP evaluates the flow as a quantum entanglement graph, it doesn't need to decrypt payloads to understand the network state. Mapping telemetry to physical geometry allows processing to occur at the speed of light, directly on the DSP hardware. This speed is critical when an advanced persistent threat attempts to infect a GPU node through lateral cluster traffic. Traditional firewalls are too slow to isolate an APT without introducing massive latency, as they must stop the data to analyze the code. The coherent DSP identifies threats by detecting structural distortion in the flow. As malicious data enters, the entanglement graph warps, measured as quantum relative entropy. The DSP reacts instantly, severing the connection and dropping the light wave to 0 watts. This creates an autonomous hardware air gap. The connection is terminated before the malicious packet can reach the switch. Securing the network through topological physics provides a zero-latency threat quarantine that software-based systems cannot match. This same tensor mathematics addresses the problem of Ethernet microburst congestion. Reactive routing logic only takes action after a packet queue has already formed and the network has slowed. A PTCP-equipped transceiver monitors its local tensor state to forecast congestion before it manifests. Running this state through a conditional value at risk algorithm, the transceiver signals the host NIC to preemptively reroute traffic milliseconds before a microburst forms. The technical framework describes this as a core feature, where the optic provides the routing intelligence to the host hardware. Moving these predictions to the optic enables the lossless, deterministic Ethernet performance required for AI backend fabrics. Moving intelligence to the transceiver alters the server rack's financial and physical footprint. Standard architectures are filled with CPU-intensive middle boxes and routing processors occupying significant space. By offloading security to layer 1 optics, operators remove these appliances entirely, significantly lowering power and cooling requirements. This also recovers compute cycles previously lost to running semantic protocols and network overhead. This capital expenditure recapture is a primary incentive for hyperscalers. The value of reclaimed GPU cycles can effectively pay for the upgrade to intelligent optics. This shift to intelligent Layer 1 infrastructure makes massive amounts of previously stranded compute power available for AI training and inference. Hardware manufacturers can no longer differentiate themselves solely through physical metrics like baud rate. Integrating the PTCP omnibus cage at the edge of the optical envelope creates a distinct separation in the market. As the source documentation notes, this partnership with Tensor Networks makes the hardware indispensable to Tier 1 hyperscalers. The integration embeds self-routing and self-defense capabilities directly into the infrastructure layer. By merging advanced photonics with topological physics, Coherent establishes a generational competitive moat in the exascale AI era.